Okay, question 2. Capillary action can cause a liquid to rise up a hollow tube. Figure 3 shows water has risen to a height of h in a narrow glass tube because of capillary action. Figure 4 shows the variation of h with temperature theta. The uncertainty in the measurement of h is shown by the error bars. Uncertainties in the measurement of temperature are negligible. You'll only ever get error bars in one direction, not both. Draw a best fit line for these data. Right, so what you have to do is you have to draw a line that goes through every single error bar. Don't just join up the first and last points, although in this particular example it's a pretty good approximation. So I think it's to be about there. So I hit that error bar, that one, that one, that one. And just outside on that one. So it takes a little bit of toing and froing. If you've got a clear ruler, it's much easier. So there we go. It is suggested that the relationship between h and theta is this, where h0 and k are constants. Determine h0. Right, so well, this is a straight line, so we've got on the y-axis h and on the x-axis theta. So we've got y is equal to mx plus c. So let's link these up. On the y-axis we've plotted h, so that's that. On the x-axis we plotted theta, so that's that, which means that the gradient must be all of that, and it's meant to be negative, which it is, that's good. And only just hit that one there. And that one is that there. Right, so determine h0. So h0 is going to be the point where it's the y-intercept there, which is 165 millimeters. So that's 165 millimeters, like so. Show the value of this is about 0.9 millimeters per Kelvin. Right, well, these are in degrees Celsius, but 1 degree Celsius is the same as 1 degree Kelvin, so that works. Right, so minus h0k is equal to the gradient. So we need to work out what the gradient is here, and we draw our triangle on here. We can pretty much draw it on the axis, or we can draw it on the axis. So that's 0, that's 100, that's 0, no, that's 80, and that's 165. So we need the change in y. Well, the change in something is always the final value minus the start value. So the change in y is going to equal 80 minus the start value, which is 165, divided by the change in x, which is the final value, 100, minus the start value of 0, which is equal to minus 85 divided by 100, with a pen, which is equal to 0.85 minus 0.85. So therefore h0k is equal to 0.85, and the units are millimeters divided by, in this case, degrees Celsius, but degrees Kelvin is the same. Determine k and state your answer. Well, h0k is equal to 0.85. We also have h0 is equal to 165. That's in millimeters per Kelvin there, so that's going to be okay. So k will equal that divided by that. So it's 0.85 divided by 165. So I get the calculator out. 0.85 divided by 165 gives us 0.00, and notice the dots there, so that's 515151. Be careful here, because when you round that to two significant figures, you get 0.0052, and the units will be Kelvin to the minus 1. Now just be really careful because that bit there rounds that one up, and lots of students miss the fact that it's got the dots on there, which means that it is a recurring fraction. Okay. Question 2.5. A similar experiment is carried out at constant temperature with tubes of varying internal diameter d. Figure 5 shows the variation of h with 1 over d at a constant temperature. So there we've got 1 over d, there's h. It's a straight line through the origin. It is suggested that capillary action moves the water from the roots of a tree to its leaves. The gradient of this is 14.5 millimeters squared. The distance from the roots to the top of the leaves of the tree is 8 meters. Right, this is in millimeters. So let's just quickly change that to millimeters in case we need it later. Calculate the internal diameter of the tube required to move water from the roots to the top of the leaves by capillary action. Okay, I don't give you much room to do this one. So here goes. First of all, we need the equation for a straight line. So y equals mx plus c. Well, y in this case is h, m is 14.5, x is 1 over d, and c is the y-intercept, which is going to equal 0. So that's just h is equal to 14.5 divided by d. We want the diameter, so let's rearrange this to get d. d is equal to 14.5 divided by h, and there's h, so 14.5 divided by 8,000. So here goes. 14.5 divided by 8,000 is equal to that. So that is d is equal to 1.81 times 10 to the minus 3. Now, d to the minus 1 is in millimeters to the minus 1, so d is going to be in millimeters. Okay, we've already switched it over here from minus 1 to just d when we did this rearranging here. So that is our answer of diameter. Comment on the accuracy of your answer for the internal tube diameter in part 2.5. Right, so accuracy, we're talking about confidence here. What's the confidence that our answer can be correct? Well, if we look here, the experiment covers values from 0 up to 200 and, what's that? It's just less than 300, so that's 290 millimeters. And we're extrapolating that line all the way up there until this is at 8,000, and that's the value that we're reading off. So when you extend a line like that to work out another value, that's called extrapolation, and it's not very good at the best of times, but we're going from 290 to 8,000, so that's a very big extrapolation. So I'm going to say that the accuracy is small, as we are extrapolating from about 290 millimeters all the way to 8,000 millimeters. The graph might be different at that point. So in other words, it might look like a straight line here, but maybe it bends up, or maybe it bends down, or maybe it just stops and you can't go any further. So that's what I would say. Our confidence in the result is very small.